So far in our discussion of simple harmonic motion, we have only considered the ideal case where the energy stays constant. In other words, there is nothing to slow down the oscillation and it will keep on going forever. This is very rarely the case, so in this video I will introduce the concept of damping. Let's say we have our spring mass system, and as we know, let's make it clear that the equilibrium position would be here, so the spring has been stretched to the right. We know that there is the restoring force F that equals minus kx, F restoring. But also in this case we have a damping force that acts in the same direction as the restoring force, which means it is opposite to the direction of movement. So when the spring is moving this way, there will be a damping force, F damping, which is opposite to the motion of the mass, and it's proportional by b to the velocity of the mass. A good example of such a damping force would be air drag, for example. That is directly proportional to the velocity, but opposite to the direction of the movement. Anyway, in this case, we see we have two forces acting on the mass. And if we write out the equation of motion and solve it, which is again a second order differential equation, we get the following result. The displacement as a function of time will be some amplitude times a new term, which is exponential decay as a function of time, cosine omega prime t plus the phase angle. The omega prime is the new angular frequency. In the non-damped case, it was square root of k over m, but in this case, the damping will change the angular frequency and the oscillation frequency by term b squared over 4m squared. The b is the proportionality constant of the damping force. And from this expression we see that whenever there's damping, the oscillation frequency reduces a little bit by this factor. The constant gamma in the spring mass system case is b over 2m. But what does a decaying exponential function look like? It will be something like this. It starts from some value and then approaches 0 as the time goes to infinity. So this would be our e to the power of gamma t. And also in our displacement we have the normal sinusoidal motion as a function of t, which is the usual sinusoidal wave. And when we mate these two, by multiplying them, as seen here, we get the displacement curve for damped harmonic motion. So in essence, it's an sinusoidally decaying, or excuse me, exponentially decaying sinusoidal wave. The rate of decay is characterized by the constant gamma, and it can be determined from the physical parameters of the system if we know them. But if you don't, we can also deduce it from the measurement of the motion. So let's say we measure the height of the amplitude here. This is called A1, and sometime later the amplitude is A2. So this would be T1, and here we would be at T2. So at any given time, our amplitude is determined by this factor. So A1 would be A times e to the power of minus gamma T1, and A2 would be A times e to the minus gamma T2. Now, taking the ratio of the two, A1 over A2, we get A to the minus gamma T1 divided by A times e to the minus gamma T2. The a's will cancel, and we get e to the minus gamma T minus T2, which is same as e to the gamma T2 minus T1. We take, to get rid of this exponent, or bring down the exponent from this side, we'll take the natural logarithm of both sides. So we get ln of e to the gamma T2 minus T1, and on the other side we have a natural log of the ratio of the amplitudes. So this simplifies to gamma T2 minus T1, same as ln A1 over A2, and further solving for gamma, ln A1 over A2 divided by T2 minus T1. You get slightly different results for the value of gamma depending on which peaks do you pick and how accurately you measure their amplitude or the time between them. But no matter what peaks you pick, you should get the result or results that are in the same ballpark. A common benchmark for the rate of decay of a signal is to say or measure how quickly the signal reduces to the e to the minus 1, which is 1 over e, of the initial value. For example, in our case, how quickly the amplitude reduces by factor, or to the factor 1 over e, which is about 37% of the original value. To this condition to be fulfilled, we see that the gamma times t must equal 1. And solving for t, we get 1 over gamma, which is usually denoted by Greek letter tau. And this is called time constant of the decay. You'll get to practice this in your homework. The damping isn't always exponentially decaying sinusoidal wave, like in this case, which is also illustrated in this figure by the curve A. Mathematically, we have different cases of damping, and it all comes down to the definition of the angular frequency. In order for this radical to be defined, the argument has to be larger than 0. Then we get a sensible argument for the cosine, and we get the curve A. But if the second term exactly cancels the k over m, our angular frequency is 0. And in fact, the movement will look like the curve B here. It will approach 0, but it never crosses below the negative direction, so it doesn't oscillate. It just decays to the steady state value in a quickest possible manner, to be exact. Also, it is possible that the B term is so large that this sum becomes negative, and that would mean imaginary value for the square root, or the calculation of the square root, and plugging something imaginary into the cosine doesn't make any sense. So in that case, the motion is not described by in a way by the sinusoidal wave function. So in fact, it will look something like the curve C here, where it takes its sweet time to approach the steady state value, which is 0, of course. We can call these 3 different cases by the following terms. This is called underdamped case, which is the most common in the simple harmonic motion that has been damped. The B would be critically damped. The damping is just enough to kill off the oscillation. And then we have the case C, which is called overdamped. The damping is way too large for the movement to exhibit any kind of sinusoidal motion. In your homework, you will only have the underdamped case A, but it's important to know conceptually what critical damping and overdamping mean.
Start to figure it